Okay, let us continue. So last time we finally started doing work in this class. Enough cruising. And we shall continue to do work, at least for the next class or two. Work.
I think it's 7.6.
It's 7.6. See, someone didn't do enough work. Okay, so this was sort of the handout I wanted to give you guys last time. So I talked about the major concepts here, which we went over last time. I can just reiterate them about what work is. As a formula, it just means force times distance. That's the case of a constant force. More general, whether your force is constant or not, you can think of work as an integral. It's the integral of force from over some distance, which is represented by the limits on your integral. So that's something nice. I mentioned here the note on units, grams, kilograms, these are units of mass. If you need to change them to weight or force, you need to multiply by gravity, which is 9.8 meters per second square or 32 feet per second square, depending on whether you're using meters or feet. Pounds is already a unit of force, so you don't need to multiply that by gravity or anything. It is force itself. If you have grams in a problem, change it to kilograms and change your length to meters, and that gives you the nice units of newtons for your force, and the work will have joule as the unit if you use kilograms and meters. And a joule is pretty much 1 Newton meter. In general, I won't care too much about the units, but it's good practice to actually know what they are, because you can actually double check your work here by looking at the units. So the first thing we went over was Hooke's law. It's very important that you know what this states. It tells you that it gives you a formula for the force when you're working with a spring, and you're extending the spring beyond its natural length. Right, so probably just recall that. Hooke's law. So I gave one example here, but your homework will have several more examples, so make sure you do a lot of practice on those. It's not difficult, but it can be kind of tricky, and the wording can catch you, so be very careful. So it says the force f of x to stretch compress a spring. I mean, you don't really have to write this down because it's here. Is given rephrase that. If f of x is the force this is a paraphrasing, then the work to move the spring from A units beyond natural length. Right, so it's very important that the number that you put down here is the difference between the starting point and the natural length. To B units beyond the natural length. Is given by kx dx, right? Since f equals kx by Hooke's law. So Hooke's law is the guy that says the force is given by this equation, so this is sort of a corollary to Hooke's law. So the integral of force, it's very important how you know to set up the numbers. We spoke about that last time. Make sure you go over that example. This is a very comprehensive example, I think. It's the same example that's here. So we did problem 1 last time, and the answer was 3375 inch-pounds in the units that I used. So we'll move on to talk about lifting problems. whole batch of chalk that they got. So basically the idea here, again I repeated here what the basic approach to these problems are. It's if you're lifting objects piece by piece, that's how you sort of want to think of them. Things like ropes or cables, something that you can't move all at once, but you move in pieces. We call those lifting problems. And basically you just figure out the work to move one infinitesimal slice. You think of one slice of the object you're moving, figure out the work to move that object. It involved choosing where your origin was and setting up the equations based on distance and force and all that. We did problem 2, which is when we had a 100-foot cable that weighs 300 pounds hanging off the side of a building, and we needed the work to lift, find the work to lift the cable to the top. We actually did that. That was problem 2. Problem 3, I said there was a bucket of negligible weight with 500 pounds of water, and it was attached to the end of the cable. What is the work in lifting that? And basically what we did there was we dissected the problem, figured out the work to move the cable, and added it to the work to move the water. Now, in problem 4 is sort of where we stopped, so let's actually do that one. And I guess in answering problem 4, I'll redo the part that we would have done in problem 2, just for you to see it again, and we can go over it and you can ask me any questions if there are any. So basically we're going to do problem 4, which is a continuation of problem 2, so let's read problem 2 again. A 100-foot cable weighs 300 pounds, hangs off a cliff, hangs off the side of a tall building. So here's our cable. It is 100 feet long. Cable weighs 300 pounds. We assume it's uniform. Hangs off the side of a building. Right? So what we did here. Now we're assuming that attached to this cable is a bucket and there's water in the bucket, right? There's a bucket of negligible weight, which means I'm not going to calculate the force for that. Pretty sure that negligible is trouble. So the cable that weighs 300 pounds, a bucket of negligible weight, its bucket filled with 500 pounds of water. It leaks at a constant rate. It's pulled up at a constant rate. And is empty by the time it reaches the top. Find the total work done. So cable hanging off the side of a building, it is 100 feet long, it weighs 300 pounds, attached to it is a bucket, which we don't care what the weight is, but it contains 300 pounds of water, which it's leaking though. And it leaks, it's empty by the time it gets to the top, we're pulling at a constant rate and it's leaking at a constant rate. How much work did it actually take to pull this up all the way to the top is the question. How much effort does it take? So, how do we start? Remember, first thing you want to do is you want to set up some variables for your distance. You choose where your origin is. You can choose either the top or the bottom. Personally, I like choosing the top bottom to be my origin and measure the distance increasing upwards. Right? So, what was the idea here? What is our work going to be? Well, how are we going to think of this? The total work, how are we thinking of this? Yeah?
The work to pull the rope plus the work to pull the bucket.
There's the work to pull up the rope, plus the work to pull up the bucket, plus the work to pull up the water, right? Now they said the bucket was of negligible weight, so we're just ignoring this, right? Because they said it's negligible. Right? So pretend the bucket doesn't weigh anything to make the problem simpler. I could have easily made it weigh something, but in this case they said it was negligible, so you can ignore the bucket part. So we're just worried about the rope and the water. So let's focus on one. Let's talk about the work to move the rope. And here's the setup. So we're only focusing on the rope. I put the origin at the bottom. And what I'm going to do is I'm going to dissect this rope into slices, and I'm going to figure out the work to move each slice one at a time, and I integrate to find the total. So I focus on one slice here, right? Whose thickness is delta x, some small change in x. And I want to figure out what is the work needed to move that one little piece to the top, right? I consider that piece to be at a level x from the bottom, which means that the distance it needs to travel to get to the top will be 100 minus x. So here I know that my distance, the way I'm setting things up, the distance to travel is 100 minus x. Then I'm going to worry about the force for this piece. Right? And we found that it was, what was it? It was 3 delta x, right? Since the unit force was 3 pounds per foot, right? So if the force is 3 pounds per foot and we have delta x feet, then the force for that is 3 delta x, right? And remember how we got this? We just put the total force over the total length to find the unit force, right? So that's just 3 pounds for every foot. So every foot of this cable we're assuming weighs 3 pounds. So if I have delta x feet, that weighs 3 times delta x pounds, right? So that was our force. So basically the work for this slice was force times distance, which is 3 delta x times 100 minus x. So the total work was the integral of this. Right? So we had 3 times 100 minus x, and our delta x, we're thinking of this as a Riemann sum, that guy becomes our dx. And the limits on our integral describes the length of the rope that we want to actually move. We want to move all slices from the level of 0 to the level of 100. Therefore, I integrate from 0 to 100. We computed that last time, and the answer was 3375. So let's continue that over here. So the setup is the important part. That integral is really not a difficult integral to do. It's just a polynomial, just distribute and use the power rule. So we know that the work for the row, not work, total. So we know that the work for the row was 3375, which was our solution to that integral. Okay, so that was our rope. That was a recap. Now we're at the end of last class. Now we're going to start to do something new. How do we figure out the work to move the water? This one is a little bit challenging if you don't sort of see what to do. How do you think we're going to attack that problem?
Can we take the derivative of it?
Gravity.
Hmm?
You use gravity.
We don't need to use gravity here. Why don't we need to use gravity?
Give me the
Huh?
Give me the pounds.
Because it's in pounds. Remember, whenever you see pounds, gravity is already factored into the problem, right? Pounds is a unit of force, which means they already did the whole mass times gravity calculation, right? So once you see pounds, you don't have to worry about gravity anymore. Right? So make note of that. The units are very important in that sense. They sort of tell you what you have to do, what you don't have to do. So gravity is not a consideration anymore. It's already been dealt with.
You calculate the work done for full water, then subtract it with the water leaving. Since it's constant rate, it's just like 500 divided by the constant rate of 2.
How would you do that? Because if you think of moving the work of the whole thing
Yeah.
minus what's leaving, well, at the end, everything left, right? The bucket was completely empty when you just cancel each other out. Thinking in terms of force, remember we're going to use, is the force constant or not here?
No.
Right, because it's heavier when it was at the bottom, it's 500 pounds. As we lift it, it's getting lighter, so we're not using a constant force. So we're thinking of work here to be the integral of some f of x dx.
Oh,
Right?
0 weight. to
Now,
500.
how are we going to figure out what this f of x is doing?
Well, the limit says 0 to 500. So it was 0.
What is 0 to 500?
The weight.
The weight, the force, okay? Sort of relate that to our distance x. How can you do it?
Use FD. The force and the distance. The force of the water, the distance between the 0 to 1.
What's the force of the water? That's the whole point. I want to know that. How do I get the force of the water? Let me ask it this way. What kind of function would describe the force of the water?
Linear.
Linear. How do you know it's a linear function that would
With
describe it?
distance, the constant.
Because things are happening at a constant rate. The kind of function that changes at a constant rate is a linear function. So I know there is some linear function that describes the force of the water. Okay? Which means I could perhaps graph it, right? Graph a straight line. What are 2 points that this line would have to pass through?
500 at the beginning and then 0.
So let's say I'm plotting my f of x, I want to be force, right? So that's my y-axis. And I want to relate that to the distance x traveled, right? Tell me, I know it's a linear function because everything's moving at a constant rate. Tell me 2 points this function passes.
Intercept, the force starting 500 and then at 200 is 0.
When x is 0, what is the force?
500. Oh,
Right, so it passes through the point 0, 500.
and
Now
this
when x is, what's another point?
100 then it's like 0.
When x hits 100, our force hits 0. It's changing at a constant rate, therefore, that's the equation of my force. How can I find a formula for that equation? Right? F of x would be, slope is
500
rise over run, right? So it's just 5. So I know it's 5x. It's negative because it's going down. So it's minus 5x plus 500, which is the y-intercept, right? Now you can notice, when my x is 0, it's 500. When my x hits 100, it's now 0. And it's changing at a constant rate. This force accurately describes the force that's being applied to moving the water itself. So what's the work to move the water? Well, it's just the integral of that function when x goes from 0 to 100. Right? So with these word problems, you have to really read very carefully. Every word is like a clue when you have constant rate. Ooh, what does that mean? Oh, it's a linear function. That's what it means. Right? So the work for the water is simply the integral from 0 to 100 of f of x ds. The integral of force gives us work. Minus 5x plus 5. Now in this way you can sort of see it as what you were thinking. It's just the work to move the total thing minus how it's leaking, but it's leaking at a functional, it's leaking at a constant rate, so that part was a linear function that you have to worry about. Anyway, we can integrate this. This is minus 5x squared over 2 plus 500x. 0 and 100. So this is minus 5 times 10,000. 2 plus 500 times 100. And 0. What's that? Did I write down the answer? Didn't write down the answer. But what's that number? Huh?
Yes. What was it?
What?
No, the first is negative. Oh, okay. Yeah.
The 2500
0,
00? That's the final answer?
No way.
No.
That looks big.
5530.
There are 3 zeros.
It's 25,000.
Okay, so, and that is, what's our units here?
Wait, it's work done, so it's pound, feet, something.
Pounds and feet, so it's foot pounds.
Foot pound.
Right, that's in the notes, by the way, on the first page. Foot pounds. Okay.
What's the unit of mass in American units? Like kilograms, and then.
There are several.
Oh, you have American?
Like you can have like what's called a slug, I think. Yeah, there are several.
What is that?
Let's see.
What?
So the total work would be what? Ultimately, total work would be the work for the rope plus the work for the water equals the work for the rope was 3375 plus the work to move that water was 25,000. Right, so that's 28,375 foot pounds. And I ask you here, what if the bucket weighs 50 pounds? How would that change the answer?
We just add another work done plus
plus 50.
a constant work done.
It's 50
over there.
Right, it would be a constant force, right? It's always 50 pounds. The mass or weight of the bucket isn't changing. So you simply add a force times distance. So you just add 50 times 100, right? To the answer. So even if I told you to actually consider the bucket, it wouldn't actually be that bad. You wouldn't even need an integral for it. Okay, let's get to the fun problems. Pumping problems. Now these are nice. They have a standard formula, but you still have a lot to figure out based on the kind of object that we're working with. Right? We're going to talk about pumping problems. Talking about things like pumping liquid or some sort of fluid through some sort of tank or object or container. Main formula. The work is the integral. Again, it's force times distance, but force you can think of as volume times density times distance. Density, the units here must be, we must think of it as force per unit volume. So that the volume would cancel the volume here and we end up with force, right? Density is the amount of substance per unit volume, right? That's the definition, right? From chemistry. If you guys remember chemistry. So that's basically the general form that we're going to be using. And I mentioned here, again in the first page of your notes that you should read through, where did I talk about it? Yeah, I mentioned here, under pumping problems, the units of density must be in force per unit volume in order to be consistent with the original formula. So for example, you would measure density as pounds per cubic feet, right? Not kilograms per cubic feet, right? Because the units actually matter here, right? It has to be force per unit volume. So you must have a unit of force over a unit of volume, which is equivalent to this unit of volume. And then this guy ends up being force. So it's the same as our previous formula. And we actually do things the same way. We talk about slices. The only difference is now is we're going to be worrying about the volume of the slice that we make. Right? So let's actually do a problem. So let's look at problem 5. An inverted conical tank is filled with a liquid that has density of 200 pounds per foot cube. That's force per unit volume. So don't need to change any units here. Don't need to worry about gravity because it's in pounds, right? So that one sentence tells me all that, right? Yeah, the tank has a height of 12. The radius at the top is 6 feet. Find the work needed to pump the liquid out the top of the tank. It's an inverted conical tank, which means it's like this. So I have a tank like this. It has a height of 12 feet. It has a radius of 6 feet. And it's filled with a liquid, right? So it's filled with some sort of liquid whose density is 200 pounds per cubic foot. So for every cubic foot, the liquid weighs 200 pounds, heavy liquid. By the way, for comparison, water actually weighs 62.4 pounds per cubic foot. Right? If you take a box that's 1 foot by 1 foot by 1 foot and fill it with water, it'll weigh 62 pounds. Right? So this liquid is actually heavier than water. Okay. So now what I want to do is I want to attach a pumping machine to this that's going to pump this liquid out the top of the tank. And I want to find out how much work will this actually take to accomplish this. This is called a pumping problem. We're pumping a liquid out of some container. So here's the idea. Again, worry about one slice at a time, right? So pretend we're taking a slice of this liquid. So we're going to slice it. Right? There's a slice of thickness delta x. Right? Again, I'm going to place my origin at the bottom. This is x equals 0. I consider this slice to be at a height x, which means that the distance it has to move to get to the top of the tank is what? 12 minus x. Okay. So far, so good. What would this slice be? What kind of object is that?
Cylinder.
It's a cylinder, right? Now, remember our formula. Work is volume times density times distance. Do you remember what the volume of a cylinder is?
Something.
130 pi squared. Wait, what were we talking about?
Volume of a cylinder. Volume of a cylinder. Pi r squared h, right? Area of the base times the height. The area of the base is a circle, right? So this guy is going to have some radius r, right?
Yeah.
And so I'm going to know that my volume is pi r squared h. What's my h in this case? Delta x. Now the problem is, x is of course my variable, which means this r is not usable to me.
But in terms of x.
I need to figure out how can I write r in terms of x.
No. Similar triangles.
Oh.
Similar triangles is the trick here, right? That's pretty much the most convenient way to do this. So the trick to this problem is to use similar triangles. Basically what you're going to do is you're going to imagine another slice cutting through this cone like a vertical plane, right? And the kind of picture you're going to imagine here is that there's a right triangle with height 12. The base is 6. And there's a part here that I want to measure whose length is r and whose height is x. Right? What I've just done is created a similar triangle. I have a large triangle and I create another triangle inside it with a line that's parallel to one of the sides. This creates a similar triangle, meaning they're proportional. The large triangle is proportional to the small one, right? Because they're similar triangles, which means the ratio of corresponding sides have to be equal, right? So if I look at the large triangle, for example, if I take the base over height for the big triangle, it must be equal to the base over height for the small triangle. What's the base of the big triangle? It's just 6. The height of the big triangle is 12. Base of the small triangle is r. The height of the small triangle is x. This means my r is x over 2. This means the volume of this slice is pi times x over 2 squared times delta x. Now I'm going to apply my formula. So this is the part that will vary from problem to problem, the finding the volume part, right? Depending on what this original shape looks like, your slice can be shaped like a cylinder or a box or something else entirely, right? You just have to know, you should draw a diagram definitely to sort of see what shape you're going to end up with, right? But you're going to have to be a little, have some tricks up your sleeve to figure some of these guys out. Anyway, so we can use the similar triangles trick to figure out what our radius is here in terms of x. And so now the work to move this slice is volume times density times distance. The volume is pi over 4 x squared delta x. The density, we were told, is 200. And the distance that this thing has to travel is 12 minus x. So this is 4 into 200, 50 times. So I can write this as 50 pi x squared times 12 minus x delta x. That's the volume to move one slice, the work to move one slice. So the total work is going to be the integral of this. 50 pi x squared 12 minus x. That delta x becomes dx. What are the limits on my integral?
0 to 12.
Right. It's filled with liquid, and I want to pump all of it out. It's 0 to 12. Now, just like Hooke's law, the limits you want to think of in a very specific way. So I'm going to tell you now. This describes the length of the liquid. The length of the liquid you want to move. When you draw the 2D depiction, as in length of the liquid you want to move. It's very important that you don't confuse that with something else, which, did I do a problem that can take advantage of that? Yeah, the spherical one. I just call it. So you do that integral, did I say the answer here? No. That's going to be the setup. That was the hardest part. I don't know, should I even do the integral? Okay, let's just sort of run through this quickly. And I want to do a variation of this. It's not on the handout, but I'll just do it. This is 0 to 12. So how do we work this guy out? Just think of it as 50 pi 0 to 12. 12x squared minus x cubed dx. this gives us what? 4x cubed minus x to the fourth over 4. 0 to 12. This is 4 times 12 cubed minus 12 to the fourth over 4. So this is 4 times 12 cubed minus 12 to the fourth I can think of as 12 times 12 cubed divided by 4, so this is 3 times 12 cubed. And so this is just 4 apples minus 3 apples is just 1 apple. So it's 12 cubed. 50 pi times 12 cubed, whatever that is. Foot-pounds.
86,400 pi.
86,400
Pi.
pi foot-pounds. Should write that down in my next version of this handout. I'm just going to tell them the answer. $86,400. Questions on this problem?
That's the amount of work for the water to drain.
To be pumped out to the top. Okay, so let's do a variation on this. There is a 2-foot spout at the top. What is the work done in pumping the liquid out the top through this spout? Right, so basically I have that inverted conical tank, but there's a spout at the top, right? The liquid is being pumped out of this, right? It's actually 2 feet high, right? Everything else is the same. This is 12 feet, that's 6 feet, radius. How does that change the problem?
Do you just set the limits? You add 2 to
From 0 to 14.
yeah.
But
What-
it's not a cone anymore, is it? What did you just change? But isn't it a segment of a cone?
So if we have this slice here, right? Same setup. So this is x equals 0. This is at a height x. Its thickness is delta x. What's its distance that it has to move now?
14.
The distance to get to there is now 14 minus x, right? It's 12 minus x plus an additional 2, right? So how would that change our work integral?
It would change your slice. Just set up for the slice.
Did you put 2 integrals, 0 to 12, 12 to 14? No?
You don't.
What actually changed here?
The height.
The amount of liquid I had to move, has that changed?
No.
No.
No, it's still just filled to the top of this conical tank.
The distance is.
What's the length of the liquid I have to move? It's still the liquid from 0 to 12. The limits on my integral won't change. That's still 0 to 12, right? The density of the liquid doesn't change, right? The setup for this disc doesn't change. Literally the only thing that changes is the distance that I'm pumping. Literally it's just going to be 50 pi x squared. Instead of 12 minus x, I will now have 14 minus x dx. And I would do that. So you really have to think, what is actually changing? But if I ask you, we only want to pump the top half of the liquid out through the spout. What limits?
No. The entire cone minus the tiny cone. Yeah. Okay.
Right?
Okay.
So I want to put some other liquid in there, so I only want to pump out half of it, like the top half.
Or never mind.
Right? So I want to leave the bottom half in and just pump out the top half. How does that change the problem? What would my work integral look like now?
Entire cone minus the tiny cone.
It's easier than that.
The lid.
Oh.
This is the volume of,
Hmm?
it's like this,
Half of the
What limits?
You can't do 6 to 12, so that will just be messed up. Or never mind.
6 to 12. Everything else stays the same.
You did not say anything.
No, it's the change the limits though.
But
Hey, your brain has something.
That's it. Remember our limits, what does the limits describe? The length of the liquid you want to move.
move, right? 6 to 12.
I only want to move the top half. That means I want to move all the liquid from position x equals 6 to x equals 12. So the only thing that's going to change here is the limits on my integral. So if I do things like add a spout, the only thing that will change is my distance. If I do things like restrict what part I want to move, the only thing that will change is the limits on my integral. Right? Every part of this integral means something. The limits on your integral describes this and only that. Right? This describes the distance you're moving, right? And this will describe your volume times density. So be aware of that. The only way this expression here is going to change is if somehow my volume changes for some reason, or my density changes for some reason, which is hardly ever the case. Usually it's going to be your distance you can manipulate, or how much stuff you want to move will be manipulated. But you should know how, just by changing a small variation to a problem, how it's going to affect the answer. Well, that just comes down to knowing the formula and knowing what each individual piece is all about. So yeah, those were a couple of variations there.
There's the 2 pump.
Huh?
There's the 2. There are 2 pumps.
Two pump?
2 spouts.
Two spouts.
Oh, that's a good question.
That is a good question. So how would you think of doing that? Then you'd have to worry, will equal amounts of liquid being pumped through each spout? You could probably just divide it into half for each spout or something like that.
Yeah, probably. The test will
Yeah, there'll be more considerations there. Like if they pump things out at the same rate and it's at the same height, it's also a 2-foot spout. You can just divide the work in half for each spout. If one is longer, then it's going to be a lot more difficult. You have to worry which one is going to outcompete the other. It'll be a much harder problem.
like in a test with 5 stars.
No, because my tests are always easy and fair.
5 stars with different.
Like exactly what I show you on the board is like exactly how the test is going to look. It's always that.
You're so good.
The other example, problem 6. Now we have a rectangular tank of length 10 meters
Rectangle keyboard.
with 5 meters, height 5 meters. It's filled with water, right? The density of water I'm giving you here, it's 1,000 kilograms per meter cubed.
Can't trick us.
So
KG.
here, just a rectangular tank, right? The length is 10 meters. The width is 5 meters. And the height is 5 meters. And it's filled with water, full to the top. Right? I gave you the density of water. Find the work needed to pump the water out the top of the tank. And here, so I told you the density in kilograms per meter cubed. And just for your edification, I told you about what it is in pounds per foot cubed. But we don't need that here. We're doing with meters and kilograms here. So what are some considerations here?
Same thing, volume density, distance, I guess.
Before we even get to that. let's just do it. So we're going to be doing work equals the integral of volume times density
Distance. VDV.
times distance.
VDVDU.
And again, what volume? Volume of the slice, right? So we're going to start to slice this water up into levels. Right, so try to put this here. So I'm going to consider moving one slice of this water here. Here, x is 0. Consider this slice as being at the height of x. Its thickness is delta x. The distance it has to move is therefore what?
5 minus.
5 minus x, because the total height is 5. Okay, so that's sort of the setup. So let's talk about the volume. What is the volume of this slice?
Length by height.
It's a box, so it's length times width times height. What's the length? 10. What's the width? 5. What's the height?
Dx.
Delta x. Okay, so far so good. So this means that my work to move this one slice is equal to volume 50 delta x
Density.
times density. What is the density here? 1,000. And what's my distance?
5 minus x.
5 minus x. Is that fine?
Too easy. Yeah. Let's see.
So we're good? Are you just saying no because I'm waiting and I'm staring at you guys?
Yes.
It's not good. What's wrong?
Oh, it was too easy.
Yeah.
Did we mess up here?
No.
Did we mess up with the distance?
The gravity?
No. Wait, what is density?
Density
That's our volume,
is
right?
in
Our density was given in terms of what units? Kilograms per meter cubed. What kind of units are kilograms? Describe.
Mass.
It's a mass. What units should our density have?
Mass or volume?
No.
Mass or volume?
Force per unit volume. Kilograms is not a unit of force. Our units for our density is off. Therefore, this 1,000 is wrong. How do I fix it? Multiply by gravity. Which one?
9.9.
9.8. Why would I multiply by 9.8? Because I'm using kilograms and meters.
Which makes
So
sense.
9.8 is meters per second squared. Therefore, I would multiply by 9.8. If I was using feet, I would multiply by 32. Right? So 9.8, because I'm doing everything in metric units here. So I'd have to put that 9.8 there because this 1,000 is not a force. That's a mass, right? Which means to get the force, I need to multiply by gravity. Mass times acceleration, Newton's second law. Okay, so now that's the work to move one slice, which means the total work. Yeah, so when I paused at the beginning and said, what's the first thing we should consider here? Units was the answer. The fact that I said kilograms per meters cubed should have like sent off a red flag. Right, because that's a mass. You have to be really careful with your units. So the work total is the integral of 50 times 9,800 times 5 minus x, and the delta x becomes our dx. What's the limit to the integral? 0 to 5. Because it's filled and I want to pump everything out. Yeah, so that's going to be 50 times 9,800. Integral of 5 is 5x minus x squared over 2 between 0 and 5. 50 times 980. 25 minus 25 over 2. Which is just 25 over 2. Which just makes this 25. So 25 squared times 9. And what's our units here? Newton meters. Or you can call it joules. Questions on that? So again, same sort of idea, volume times density, but you have to watch out for your units. They'll catch you with that. You need to make sure things are in units of force and a length. If they give you mass, you have to convert it by multiplying by gravity, which will depend on the unit of length that you're using. Okay. So problem 7, they don't really do problems like this anymore. This is from previous time, but let's just do it anyway.
You're old.
Yeah, we're old-fashioned. This is one of the harder problems, I think. Well, to figure it out for the first time. It's kind of hard. We have a spherical tank. So we have a tank that looks like a sphere. The radius is 10 feet, so this is a 10-foot tank. Radius is 10 feet. It's filled with a liquid of density pounds per foot cubed. Pounds per foot cubed, so everything's in forces, and the length is in feet, so we don't have to worry about gravity or changing anything. That's good. Okay. It's filled with this liquid, right? So it's completely full of this liquid. So it's not half full, it's completely full. It has a 5-meter spout at the top.
It's orange.
So it's an orange with a spout, like a straw. A very large orange. 10-foot radius orange. Okay. Find the work needed to pump the liquid out of the tank through the spout. Ideas?
Same thing, man. What would be
Yeah, slice it, right?
Yeah.
So take a slice, let's say we're below the radius. Alright, so how does this work? This is what? The radius of this slice, let's call that R. Thickness, delta x. Again, I can put my origin at the bottom. This is at height x. The distance that's left to move is what?
It's 25. Well, I mean 10, 10, 10, then 5.
Right, there's 10 plus 10, so it's 20 feet and 20 feet. Did I say 5 meters? Yeah.
Tricky.
I meant to say 5 feet.
Oh.
Okay.
Not you.
To change meters to feet.
I don't even know the conversion.
Yeah, I don't remember either. I'd Google it.
You see that phone?
Like, yeah, like something like that, I'd tell you if I wouldn't ask you to convert that though. But that's the kind of thing that someone has to tell you. No one's gonna remember that. Okay, so yeah, so it's a 20-foot diameter plus an extra 5 feet, right? So this is a whole length is 25. So it's gonna be 25 minus x. Okay, now we have that same problem, right? The volume, this is going to be cylindrical, this slice, right? So our volume is going to be pi r squared delta x. Now the question is, in this case, how do we find the r squared? Can't use similar triangles again. There's no triangle.
The radius stays constant, so we can use the
No.
pi.
The radius isn't constant,
No. No, no.
right? But the slice is down here, the radius is smaller.
No, we make triangles. We did this in physics, I remember. The radius is always constant, it's always 10. So it's 10 minus x squared, square root that. That will be the r or something. Never mind, I'll shut up.
What are you talking about?
Right, yeah, in physics, to find inertia, we have to split this into this
Huh?
Draw a triangle from the
center.
is one side, a line from the center of the sphere to the end.
to the end, which is always constant.
You're saying the slice here?
No, Yeah, okay, for instance,
There's a
the
right
R
triangle.
Like this.
Where's the right triangle?
Down.
Down.
From the
Connect
center to
to
where?
a chord, yeah, connecting to the edge of it. So that's always 10. And
That's
then
going to be
just-
10? How do we know that's 10?
Because that's,
That's
the
the
radius.
Ah. Okay. And so what else do we know?
There was a
The height.
The
will
height.
be-
What is this?
10.
No, it's Pythagoras.
This
Pythagoras.
It's not
10 squared
This
minus
is R.
10
Oh.
squared
What's
minus
this height?
x. We can consider x or z or something.
No, x is the height here, remember?
So 10 minus x. I mean,
So the x, this is 10 minus
Minus
x,
x.
yeah.
right? Because the radius is 10. So this whole thing is 10. This is at a height of x, so that's 10 minus x.
Yeah.
Which means we've extracted a right triangle from this. 10r and 10 minus x.
Minus x, yes.
Which means what to us?
You know, r squared is like
What's it
10,
called?
10 squared minus 10 minus x.
Yeah,
squared.
Pythagoras is there.
Yeah. I was the first one to solve this and get the gift.
Right?
Congrats.
So I know that r squared is equal to 10 squared minus 10 minus squared. We can probably simplify this. So this is 10 squared minus 10 squared plus 20x minus x squared. 10 squares would cancel. It's just 20x minus x squared, which would be, yeah. Right? So that's my r squared.
Then just
So now I just substitute that into the volume.
plug and chunk.
This means my volume is pi times r squared, which is 20x minus x squared times delta x.
No, it's good.
Where did 20?
Oh yeah, no, sorry, yeah.
Yeah, because this is already r
R
squared.
squared, sorry. Yeah.
So now my work to move this slice is going to be
Integral of 0 to 25.
this is volume times
Density.
density. What was the density here?
20.
20 pounds per foot cubed. That's already pounds per foot. That's already a force per unit volume. Times distance, which we
25
was
minus
25 minus x. This means the total work pi times 20x minus x squared times 20 times 25 minus x dx. Limits
0 to 20.
0 to 20 because it's a sphere.
0 to 20, right? Remember this, it's the length of the liquid we want to move. The 5 is irrelevant. The liquid is filled to the top of the tank. So I only want to move from 0 to 20. So that's that.
Don't fuck it. Don't.
That's yeah, you just expand the brackets and do the power rule. It's amazing. In chapter 6 we learned to do all these crazy integrals and then we get to here and it's like, what? why do we, yeah, in Calc 3 and the rest you'll see why we did all that. But of course by that time you all forget everything. It's not fair. Like I asked my Calc 3 students some integrals these days and I'm like, my Calc 2 students could do this. What's wrong with you? It's like
teach this
super
first
easy.
then?
They'd have done this in like 10 seconds.
It's a money-making scheme. College.
Another example.
Go die.
A right cylindrical tank has a radius of 3 meters and a height of 6 meters. That's the meters, not inches. That's a block on the paper, if you have it. So this is a right circular tank.
Conversion.
So it has
Is it a type?
radius 3 meters, height 6 meters, filled with a liquid. You know that the density of this liquid is 10 pounds per meter cubed. That's pounds already a unit of force per unit volume, so we don't need to do any conversions, don't care about gravity or anything. Find the work needed to pump the top half of the liquid out the top of the tank. Set up. Slice. Always go. Just judo chop. Let me set it up.
Delta X.
Delta X is the thickness. What else?
X is on the origin.
Set up our origin.
6 minus X.
Distance to this, call it X.
And the top is
Distance to get up here,
3
6 minus X. So all of that is from our diagram. Right, okay. So what do we have to worry about here?
Nothing.
What do you need to compute? So we know the distance, we know the density, what's left? Volume, figure out the volume. What's the volume here?
Tiny so that
The 3.
Pi times
Is it 3
r squared, what's our h?
Delta H.
Delta x.
Oh yeah.
Can I write r in terms of x?
Isn't the rate constant?
What's the r?
3.
It's constant, so right circular cone. It's always 3. So I can, this is just pi times, this is just 9 pi delta x. Right? So our radius is constant here. Radius is constant. It's a right circular cone. R equals 3. So that's just 9 pi, that wasn't so bad. So now we're going to plug it in. Our units already match up, we're already in pounds, so we don't have to worry about gravity. So now we're just going to plug in. The work to move that slice of water is going to be volume times density, which is 10, times distance, which is 6 minus x. So the total work is the integral 90 pi times 6 minus x delta x, and this goes from 0 to 6, right?
3 to 6.
3 to 6.
3 to 6, right? The question says to pump the top half out, right? So that means from the level of 3 and higher. So the limits on my integral always describe the length of the liquid I want to move. So the top half is just from level 3 to 6. And that's going to be my integral. So 90 pi times 6x minus x squared over 2, between 6 and 3. 36 minus 36 over 2 minus 6 times 3 plus 902. And that's what pi, the units are going to be meters, pounds, right? Which is crazy. Mixing metric and imperial.
405 pi.
Unite. What?
405 pi.
405
is that already going?
pi.
Doesn't make sense.
That's the kind of thing when you write it, you're on a test. No way that's right. And then you erase everything. And then somehow you figure out how to change this to like some like newtons, and they're like, what the hell are you doing? Yeah, threw that one in there. Here's one, our last example, which actually I have more than enough time for this. Our last example is actually from an old final. This is from spring 2008. It was problem 7. I don't know if that final is still up. It probably is. But it's a nice problem. I might do something similar to this. But yeah, you'll notice that there are many different variations here, and in your homework you'll see a lot more. The shapes can vary. You can have trapeziums, triangles. Like you'll have to remember all those formulas for all that sort of stuff.
Please don't.
What's a trapezium?
This one though, something like this. Right, so if you're doing a trapezoidal prism, right, so you want, if your slice looks like this, you need to know the area of a trapezoid to figure out the volume. All right, volume of a prism is just the area of the base times the height. That's a general formula. Anyway, I'll draw the diagram because I couldn't put it in here. So it says we have a 10-foot long tank. The height is 4 feet. It has a vertical cross section of y equals x squared. So the tank looks like this. So it looks like y equals x squared, but it's 10 feet long.
Yeah.
So it's not circular. It's actually y equals x squared. And its length is 10 feet. It is 4 feet high. And it's filled to a height of 3 feet.
Can I say something?
Yes.
See the problem number 8 and see what you give in the exam. See how simple this is, and this is what comes in the exam.
What?
This is the problem you showed us. It's just a simple, 6 minus x integration, and this is what comes in the exam. There's this parabola thing. It is not full. It is.
Well, at this point, this is now an example that you've seen in class, so it's more than a fair
Then what do you
kind of problem to
expect?
put in an exam. No, it reminds me of those memes where it's like in class,
Exactly.
on homework, in the exam.
Calculate mass of sun.
Calculate the mass of the sun. If John has 3 apples in front.
It's not even full.
That's not even funny. I was thinking of putting that meme on the next test.
Oh, you ruined it. I didn't.
You ruined it.
No. I'm definitely going to put one about Thanksgiving for your test when you come back. Anyway, so yeah, this was actually a problem on a final. They described the tank this way. Height is 4, but they only filled it to 3.
Why? Why?
Just because. Right? It's 10 feet long. It's filled to the liquid, we know it has density. The liquid density is 30 pounds per foot cubed. That's mercy. Don't have to worry about gravity. So yeah, set up the integral to compute the work necessary to pump the liquid to the top. And use the integral. So you read that and you're like, oh great, I only have to set up. And then they add, use the integral to actually compute the work. Okay, so ideas, how do we do this?
Don't do it.
Slice!
Jhevon, take it.
Just take it. I'll get it back in the bonus, it's fine. Yeah, again we compute a slice.
Yeah, it's not a cylinder.
It's not a cylinder, it's correct. What kind of slice would it look like?
Trapezoid, that's what you were explaining. That's
Nope.
No, a rectangle.
It's rectangular, exactly. Length times width times height. Pretty simple. Yeah. Volume is length times width times height. Length, 10, yeah?
Yeah.
Here if I let x equals 0, this is at a height of x. Thickness is delta x. Yeah, height, delta x. What's the width?
Changing with the function of x squared.
How would I do that?
The height x is your input, and then the width will be x squared.
Well, the height would sort of be the output, right? It's probably because they describe this in terms of graphs, I should probably describe height in terms of y. It's not going to change things.
Oh,
Just call this y,
yes,
y,
yes.
delta y.
That's better, yeah.
Right? So I can literally imagine that there's the y-axis here, and the x-axis is going across here.
Calculate half of it.
So what I have here is just this shape. That y equals x squared, and then there's y equals 4, because it's at a height of 4. Right? So this is y equals 4, y equals x squared.
Let me kick it.
Now what I want to figure out is what is the length across this guy.
We can use what we learned. Find the area of two. No? Maybe? I don't know.
I just want to find the length of this guy. Tell me how would I figure that out?
Oh, yeah, 2x. Yeah,
Right, the length here is just an x value, right? So the length here, it's symmetric, that's also an x value. So the length is going to be 2x. Right? So the length across is 2x. But my variable is y, right? I'm measuring height in terms of y. So how do I convert that 2x to y?
Half y.
This horizontal length is measuring between what function? The parabola, right? So what is my x? Square root of y. Right? Because from here, y equals x squared just means that your x is plus or minus radical y. So the distance here, this would go up to radical y minus radical y. So if you take right minus left, it's radical y minus a minus radical y gives you 2 radical y. So that's actually my width. So my volume is length times width times height, which is delta y. So what's the word to move this slice?
Plug and chuck.
Plug and chuck. We know it's volume times density times distance.
Okay.
Volume is 20 radical y delta y. The density is 30. The distance from this level to the top is what? 4 minus y. This means that the total work is, what's 20 times 30? 600?
Yes.
Times the integral of radical y times 4 minus y dy is what this delta y becomes. What are the limits on my integral?
0 to 3.
0 to 3, right? Because that's the length of the liquid that I want to move. It's only filled up from 0 to the level of 3. So that would be the integral. That's the setup, and you just evaluate it. Just expand, do the power rule. Treat that as y to the half. So this is just 600, 0 to 3, 4y to the 1 half minus y to the 3 halves dy. Add 1 to the power, you get 3 halves. Divide by new power, you get 2/3 times the 4. Minus, add 1 to the power, you get 5 halves times 2/5. Means 0 to 3. And so now we have 600 times 8 over 3 times 3 to the 3 halves minus 2 over 5 times 3 to the 5 halves minus 0 to 0. And what's the units here?
Work done, so it's foot pound.
It would be foot pounds. Because our lengths are feet and pounds is our unit of force.
That's-
That's it. That's work. Those are the general principles. In your homework, you'll see other shapes that you have to try to figure out. But this technique actually works in a lot of cases. You'll be surprised. Just if you don't know what to do with a shape, just think of putting it on the XY plane and sort of calculate the equations of the curves that you can use. It's actually something you can use a lot of places. You could have even done this with the other shapes that we've been using. Now we're going to start a new topic, chapter 9. No, you guys are too excited. I'm not gonna do it. Not gonna do it. Okay, so homework for the work is due next time. So do chapter 7.6. Try out those problems. Work is guaranteed to come on your final, so it's something you should know.
That's a shock.
And yeah, we'll stop there today.
Okay, thank you.
If you're confused, it's fine. It's one of those topics that's kind of hard to get in the groove of, but once you sort of see it, you'll notice that we sort of do the same thing all the time. You'll get used to it by the time you get through the homework.
And then